Last time we looked at how to evaluate the terms of a sequence given the formula. Today we're going to look at how to go backwards, meaning if I have the first couple terms of a sequence, can I write its formula? And then we'll look at the definition for factorial. Yeah? Okay. So the question for today is, how do I write the equation given the sequence? How do we write the equation given the first couple terms of a sequence? How do we do that? And the answer depends on what type of equation that I want. What two forms can my equation take? We have two types of equations or formulas for sequences. We just talked about them in the warm-up. Explicit and recursive. Very good. So I need to look at both. So, is it what? Yes, it is. We're going to look at both. And we will start with explicit. Those are more common. It is more common when you're given a sequence to ask for its explicit formula. So, the first thing that I would recommend doing if you're asked to write an equation, explicit equation for a sequence, is look for a pattern in the signs on the numbers. The signs on the numbers tell me something important. If my numbers start out positive and then slowly decrease and become negative, meaning I'm looking at a decreasing sequence, I know I'm likely subtracting each term, right? Getting smaller and smaller and smaller. If I start negative and get positive, I know I'm likely adding. My number's getting bigger, bigger, bigger. If my sequence is alternating in sign, negative, positive, negative, positive, negative, positive, I know that I have -1 to a power. Because we just saw that in our last example when we were given the equation. There was -1 to the n, and we watched our terms go back and forth, plus, minus, plus, minus. So the sign is going to tell us increasing, decreasing, or alternating. The next thing we're going to do is look for a pattern in the numbers, detached from the sign. And there is a special case. It is possible that we are looking at a sequence that is a sequence of fractions. If they are fractions, you are going to look at the numerators and the denominators separately. There may be different patterns for the top and the bottom. Very first thing we do is we're looking for all of the possible patterns that we can see, first in the sign, then in the numbers. What patterns do I spot?
Well, how do you know if it's a pattern?
So patterns like, I notice that my numbers are doubling every time. I started with 2, and then I have 4, and then I have 8, and then I have 16.
But you can predict it.
Yeah, or the gap between the numbers is the same, 2, 4, 6, 8, 10. So things that I easily recognize as repeating. Yeah. Once I've identified those patterns, I'm going to try to piece them together to form an equation. So the next step is going to feel a little weird. We're going to guess at an equation. I don't know if it's right or not. I'm going to use the patterns and try and build one. Guess at an equation. Based on my patterns, I'm going to try and build an equation. And then I'm going to test that equation by finding the first couple terms of the sequence. Come on, pen. It happened this morning too. It crashed in third period. I'm not having a good day today with technology. Yes, because she just got back. It's hard to maintain these while I'm teaching. All right, so we're going to do some examples practicing how this works. Let's see what this looks like. When I'm doing this, as somebody who's been doing math a ridiculously long period of time, I like to label the terms so I can make connections between where I am in the list and what my team looks like. So I know this first term is A1, N is 1. A2, A3, A4, A5. Because ultimately, I want to be able to connect where I am in the list to what the formula for that term is. That's the ultimate goal for an explicit equation. Looking at that sequence, e to the 7th, e to the 8th, e to the 9th, what patterns do you see? Raise your hand when you think you spotted a pattern. Yes, sir. What do you see? E is the natural base, 2.5 something, 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 something. It's just a number. Good. Same base, exponent increases by 1. That's perfect. That's perfect. That gives me a great idea for what my function is doing. Based just on that information, I know an is going to be e to the something involving n, because n increases by 1 every time. 1, 2, 3, 4. So if I put an n up here, that's going to accomplish the increasing by 1. But right now that equation doesn't work, because when n is 1, I get e to the 1. What I actually have as a first term is e to the 7. How do I fix that discrepancy? How? What do I do to this number down here to turn it into that number there? Close. Plus 6. I think plus 6. 1 plus 6 is 7. 2 plus 6 is 8. 3 plus 6 is 9. Right? 4 plus 6 is 10. I think that plus 6 works. And I check. Yeah? A1 would be e to the 1 plus 6, which is e7. That checks out. I need to check it for a couple more terms and make sure it checks out for all of them. So A2, e to the 2 plus 6 is e to the 8. That checks out. So I suspect I've identified that pattern correctly. It's e to the n plus 6 power. Right? Because at A5, 5 plus 6 is 11, and I should have e to the 11. That checks out. Yeah. Good. If it didn't work for those terms we checked, we go back to the drawing board. We remove the plus 6 and we try something else. So some of this is going to be guess and check, right? And the more you do this, the more you practice, the faster you're going to get at recognizing those patterns and what they turn into when you put them in equation form. So that's why that practice is important. We're going to try 2 more. Yeah? Oh, come on, pen. Grr. So our sequence is -2 25ths, -2 1/25ths, -2 6/25ths, -2 and 3,125ths. Okay, let everybody copy it down first, and then you can be the first to give me a guess at it. Okay, Bruno, what do you see?
Is it squaring by 5 each time?
Ooh, so we are on the bottom multiplying by 5 each time. I agree. So this was times 5, not plus 5, times 5. Come on, Mr. J. Good. And then times another 5. I agree. So we know in the denominator, we're multiplying by 5 each time. So this is likely a power of 5. Power of 5 in the bottom. What do we notice about the numerator? Constant. Yeah, numerator is constant. So let's use those 2 facts to guess at a formula. It doesn't have to be perfect. We're going to take a guess at a formula, tweak it, get it to match. So I suspect that my formula for AN is always going to have a -2 in the numerator, because every term had a -2 in the numerator. I know that the denominator is a power of 5. And my default numerator is always n, and then I tweak it to fix it. If I leave my formula like this, and I plug in n is 1, what do I get as my answer? A 5 on the bottom. 5 to the 1 is 5. Yeah. What should I have in the bottom? 25, which is 5 squared. This power is 1 too small. I need to add 1 to it. So that in position 1, I have a 5 squared. In position 2, I have a 5 cubed. I'm going to check and make sure that I guessed correctly by finding 1 plus 1 is negative 2 over 5 squared, which is 25. Check mark, happy face.
If you didn't have that 1, it would just be 5.
Correct. It would just be 5 to the 1, which is 5. We have to have the plus 1. Yeah. So that plus here is shifting our pattern so it matches up where we are in the sequence. Good. So A2, numerator is constant. Denominator is now 5 to the 2 plus 1, which is 5 cubed. What is 5 cubed? 125. Correct. If we had started at negative 2 over 5, we wouldn't need the plus 1. It would be situated. But correct. We started ahead, so we had to account for that. Very good, Bruno. Good. We looked at the numerator and denominator separately. They behaved independently, and so there were 2 different patterns. Constant on top, power of 5 on bottom. Good. One more. Wait, did I do that right? 2, 3, 4, 5, 6, not 7. Why can't I count? Mr. Jolliffe, I know. So, our sequence, negative 2/11, positive 3/13, negative 4/15, positive 5/17, negative 6/19. The pattern keeps going. First reminder, in that step list, the first thing I look at is what's going on with the signs on my terms. What's happening here? They're alternating. Very good. This is an alternating sequence. I know when I see an alternating sequence that I should have a power of -1 somewhere in here. Because if I have a -1 to the end, odd locations have negative answers. Even locations where I have paired up negatives get positive answers. So anytime my signs are alternating, it's going to be a power of -1. Sometimes it'll be power of n. Sometimes it'll be power of n plus 1, depending on whether that first term is positive or negative. Good. What else do we see in those fractions? Ignoring the sign, we've taken care of the sign. What else do we see? Denominators. What are the denominators doing? Denoms are increasing by 2 each step. Good. What about the numerators? Good morning, Ellie. Ignoring the sign, it's increasing because it's going bigger every step. Bigger by how much? 1. Uno. Yeah. By 1. I know that the steps between each term turn into a multiplication problem when I write my equation. So these 2 numbers are going to become multiplication in my equation. So let's take a guess at our equation based on what we see. So A sub n equals, and I know that I need that minus 1 to the n to account for the alternating sign. I know this is a fraction because I have a numerator and denominator. Okay. In the top, the gap is 1. I'm multiplying by 1. That's just n. So I know there's an n here. But if I just left it as n, my numerator would be negative 1. It's not negative 1. It's 2. How do I get from 1 to 2? Plus 1. Yeah, this is n plus 1. Because that way in location 1, I have a 2 on top. In location 2, I have a 3 on top. In location 3, I have a 4 on top. And that matches what I see. Good. In the bottom, the gap between the numbers is 2. So I expect to have a 2n. In position 1, I do not have 2 times 1 in the bottom, because that would be 2. I have 11. What do I have to do to turn 2 into 11? Plus 9. Yeah. And we check. We're going to go through and check. So we're going to check A1, A2, A3. So negative 1 to the 1th power times 1 plus 1 over 2 times 1 plus 9. 1 plus 1 is 2. 2 times negative 1 is negative 2. 2 times 1 is 2. 2 plus 9 is 11. Matches. The question is, does it, we know it does because we built it that way, does it work for 2 and 3? So let's check. We like to check. A2, same process. Everywhere there was a n in my formula, I'm replacing it with a 2. That's good. That's why we're practicing a second day. Takes time. Negative 1 squared is positive. 2 plus 1 is 3. Numerator is 3. Denominator 2 times 2 is 4. 4 plus 9 is 13. 3/13. Does that match that second term? Yes, it does. I am pretty sure that this formula matches my sequence. It's correctly predicting the terms in the order that I see them. Yeah. We're looking for patterns in the numbers because that tells me whether I need one of those negative ones to the ends or whether it's increasing, I'm adding, decreasing, I'm subtracting. Yeah. If the gap between the numbers is the same, that usually means multiplication by that number in my equation. So if the gap was 3, it would be 3 times n. The gap between numbers was 5, it would be 5 times n. Whatever that gap size is, it turns into multiplication by n. Yeah? Okay. Ready? Yeah. One more for recursive, and then we'll look at factorials, and then we will be done. Yay. All the way back up here. Recursive is trickier. It was easier to evaluate. It's harder to predict the equations. This is a lot of guess and check here. Recursive equations need 2 pieces. What 2 pieces do I need? I know I need a formula that depends on the previous term. There should be an a to the n minus 1. What else do I need? I know my next term is twice my last term. What else do I need? I know I double each step. What else? If all I know is I double my number every time, can I reconstruct the list? No, what am I missing? Yeah, I need a term somewhere in the list. Yeah, good. I need a starting point to build on. Good. So the very first step with recursive is identify your starting point. That starting term is your A1. Yeah? And you're going to write A1 equals and then write the number. This should be, in most cases, as simple as looking at the first number in the list they gave you. Right? This should not be tricky. Whatever where you started in the list. Huh? Always. Because remember yesterday when we defined sequences, it was an ordered list of numbers. You wrote it down, didn't you? Oh, frowny face. So you're going to look at your friend's notes and notice that when we define sequences, it was an ordered list of numbers. So yes, always in order. Always, always. Second, I am looking at how the terms relate to the next term in the list. I'm not looking at how they relate to where I am in the list, but what do they look like compared to the previous term? Am I adding 3 each step? Then it's just a to the n minus 1 plus 3. Am I multiplying by 2? Am I changing sign? What am I doing? Once I think I found the pattern between the terms, I'm going to do the last 2 steps that I did for explicit. Guess at an equation, test it for a couple terms, and make sure it gives me where I'm supposed to be. So these 2 terms, where is my little boxer here? These 2 terms should be the same. Those 2 should be the same. Yes. Yay for technology.
You just copy and pasted it?
I did. Yeah, I was about to say, you could just circle it and make an arrow to the next column. You don't have to recopy. I am lazy. And I'm sure after you see applications, you are all lazy too, and that is fair. So we're going to do an example here to see what it looks like for recursive formulas. So same idea, we're writing a formula, but we're writing a recursive equation and not an explicit. You want to keep that in mind. That is a weird pattern. It is a weird pattern. And that's okay. That's okay. So our sequence is 971, negative 17, negative 71. Presumably it's going to keep getting more negative and more negative as we go. And in this case, I am not looking at comparing n, which is 1 to 9. I'm looking at comparing 9 and 7. How did I get from 9 to 7? How did I get from 7 to 1? So the first thing I do with recursive is I look at the gaps in the numbers. So looking at these gaps from 9 to 7, what did I do? Minus 2. 7 to 1, what did I do? Minus 6. 1 to negative 17. Pretty sure that's negative 18. See, I can do math. This next one Y'all have calculators. It's pre-calc. Double check my math. I'm pretty sure we subtracted 54. Not a pattern there. Those gaps aren't constant. There is a pattern in the gaps. What am I doing to get from -2 to -6? What about 6 to 18? Yeah, I think that's a more consistent pattern. 3 times 2 is 6. 3 times 6 is 18. 3 times 18 is 54. So I think that these gaps are being multiplied by 3. That tells me that I'm likely multiplying the last term by 3 to get to the new term. Yes. If we were writing an explicit formula, yes, we are writing a recursive formula. Because you're trying to write it in terms of the location in the list. We want to write it in terms of the previous term. So what I see here is I see my pattern for A1 I know is 9. AN is probably 3 times my previous term. I know there's another piece because 3 times 9 is not 7. What is 3 times 9? 27. So 3 times 9 is 27. I don't want 27. What do I want as an answer for that second term? I want 7. What do I have to do to turn 27 into 7? Subtract 20. I suspect my formula is probably this. I'm going to check it. I want to check it. Gave me the right second term. Will it give me the right third term? So we're going to make a list of our first couple terms. We know A1 is 9. We know A2 is 3 times 9 minus 20, which we know is 7. We just check that. A3 would be 3 times what? Good. Very good, Gerardo. Previous term. Pulling down my previous term. 3 times 7 minus 20. What is 3 times 7? 21. This is 21 minus 20, which is 1. Does that check out? Yes. That is my third term. So I suspect that this is my correct pattern. Recursive is a lot harder to write than explicit for exactly that reason. On your final, I'm not going to ask you to write a recursive formula. I'm going to ask you to evaluate one, meaning I'll give it to you and then ask you to fill in the terms. I will not ask you to write the formula for one. No, no, no. Yes? Huh? Not next week, but the week after. Next week is review. For the final, on Monday, I'm going to give you the review sheet and the practice problems. Yes. Yes, Bruno.
Next week, are we in like individual study time, or is it gonna be like fast?
I'm going to pass out practice tests and study guide. We'll do a little bit of both. We'll do warm-ups together and then individual study time after. So a little bit of both.
Okay, cool.
All right. Last thing, we need to introduce factorials. We have time left. Don't be pushing me. All right. We got time. All right, we're going to start with an example. Before we do, can I get a thumbs up if you have worked with factorials before in a math class? And there should be exactly 1 thumbs up in this class because I have an AP Stats student here and we saw them in AP Stats. For shame, Gabe, for shame. So I'm going to define some examples and we'll see if you spot the pattern. 5 factorial. Factorial is an exclamation point, by the way, just for funsies, you know, because mathematicians are sad. 5 factorial means 5 times 4 times 3 times 2 times 1. Factorial function, that's what it means. 4 factorial is 4 times 3 times 2 times 1. What is 3 factorial? Yes, 3 times 2 times 1. We're taking the number. We're only looking at counting numbers. We're taking the number, we're multiplying it by all the counting numbers less than it, all the way down to 1. Good. So 10 factorial would be 10 times 9 times 8 times 7 times 6, all the way down to 1. Good. So I'm going to write the formula for it. Define it. Yeah? Come on. Come on, please. Would you cooperate today? Okay. So n factorial is n times n minus 1 times n minus 2 all the way down to 2 times 1. Formal definition. There are 2 pieces you need in addition to that do not match that pattern. And that is 1 factorial and 0 factorial. Those are definitions. 1 factorial is defined as 1. Kind of sensible. 0 factorial is also defined as 1. Definition. In order for this definition to work, we need those 2 to start. By the way, you will notice that this list, if I come back up here, notice that this is 4 factorial. So 5 factorial is 5 times 4 factorial. 4 factorial is 4 times 3 factorial. 3 factorial is 3 times 2 factorial. So they are recursive. They're nesting functions. The next one up is the last one times the new number, which is why we're talking about it with sequences. Our warm-up tomorrow, not tomorrow, Thursday, we'll take a look at a sequence defined by factorial functions, and then we will start talking about conic sections. Yay! That is parabolas, circles, hyperbolas, and ellipses. Ellipses, as in the orbits of planets, for those of you who like astronomy and astrophysics. Don't drop out of college. College is fun. College is more fun than high school because you have more control over what you take and when you take it, who you take it with. So that freedom kind of, it tends to inspire more learning than high school does, where you're all stuck in the same classes whether you want to be or not. Yeah.